Hello, today I want to talk about a physicist's best friend, the laser. Now, I don't mean to generalize, but I've never heard a physicist say, "Come on man, put that laser away." Let's start off with the name. Where does it even come from? The word laser is an acronym for light amplification by stimulated emission of radiation. Wow, that's a mouthful. So let's break down all of those fancy words so we can begin to understand how lasers work, why they are useful in so many industries, and why physicists like myself love lasers. Light amplification refers to the intense monochromatic light that is produced and amplified by a laser, where monochromatic light simply refers to the fact that the light has a single wavelength, meaning that it only has a single color, like red, green, or blue, like the lasers I have in this photo. That's pretty straightforward, right? What about stimulated emission of radiation? What does that mean? Let's consider solid state lasers, which are like the ones that I own. These sort of lasers produce their light using a lamp and a solid crystal embedded within the laser. When I place a battery into this laser, I'm providing the system with a form of energy. This energy is used to power the lamp, which pumps light or photons into the solid crystal within the laser. Let's keep in mind that the crystal and lamp I have here are just visual representations. This little green orb here is what I'm using to represent the electron belonging to an atom of a solid crystal. The red sphere in this image represents a photon being pumped into the atoms of the crystal. The incoming photon excites or stimulates the electron, causing it to jump to a higher energy level. When the electron eventually falls back down to a lower state of energy, it emits a photon whose energy, delta E, directly corresponds to its wavelength. Long story short, a stimulated electron emits radiation, aka photons. Now that we got that out of the way, let's briefly discuss how lasers work. This is a diagram that simply represents what's inside of the laser tube. Number 1 here is what's called the active lasing medium. This is what basically contains the atoms of the solid crystal we were talking about earlier. Number 2 here represents the photons that are being pumped by the lamp into the atoms of the solid crystal. Number 3 represents a fully reflective mirror, while number 4 represents a partially reflective mirror. Do you remember the animation where I spoke about stimulated emission of radiation? That's basically what's going on inside the laser, but think about it on the scale of billions of photons. Those photons are reflected back and forth between the fully reflective mirror and the partially reflective mirror. This in turn causes the emission of more photons until the light escapes from the partially reflective mirror. This is what we see as the laser beam. Different lasers can be used for different purposes. One of the most characteristic and defining features of lasers is that some of them can have really high energy outputs. For example, the high energy output of a laser is utilized in CNC laser cutting machines. These kinds of machines use high-powered lasers to cut through materials such as wood or metal to make precision cuts. I purchased this low-powered laser on the internet, and I'm going to demonstrate just how powerful these can still be. I feel like for safety reasons, I should tell you to not try this at home. Isn't that super cool? Some of you may be asking yourselves, I wonder if that burns your skin. And yes it does. I only did it for science. Some of you may have seen those time-lapse videos of telescopes tracking the night sky. Well, this is my rendition of it. Sometimes in these videos, you'll see astronomers point laser beams to fixed locations in the sky. Have you ever wondered why they do that? As we know, the atmosphere is composed of air molecules that are constantly in motion. The turbulence in the atmosphere actually distorts incoming light from other stars, planets, galaxies, etc. This distortion is what astronomers call scintillation, or some of us call it twinkling. To deal with this scintillation, astronomers use laser beams to calibrate the optics inside of the telescope to ensure that they have the best image possible. Do you really need another reason for me to convince you that lasers are awesome? Okay, well, here you go. Have you ever struggled to measure the width of a hallway using one of those pesky tape measurers? What does that say? 3 feet, 4 inches? That's 3.3 feet? I'm just kidding. Tape measures are pretty useful for certain jobs. I'm sure that in a lot of construction jobs, they use machines like this one. This machine uses a laser to measure distance. Isn't that pretty cool? Yeah, that's right, 3.3 feet. This device emits a laser beam that travels a certain distance before it reaches a certain object. The laser beam is then reflected back and measured by the device. Using the simple formula distance is equal to speed multiplied by time, we can calculate the distance the laser beam travels because we know its speed is the speed of light and we know the time interval between when the beam was emitted and when it was received. These are only some of the applications of lasers that I think are really cool. There are so many, and I hope you take this time to reflect and think about how cool lasers are.